So the first constellation is Aquarius. And in Aquarius, we have the Helix Nebula. The Helix Nebula is a planetary nebula with a white dwarf stellar core in the middle. This is the end result of a progenitor star, sort of sun-sized, that evolved off the main sequence, became a red giant, and eventually it collapsed and formed a white dwarf core and a planetary nebula. Now, to get to that stage, the star, obviously, at first it runs out of hydrogen fuel in the core, so fusion stops. There's no more hydrogen to fuse into helium. The star begins to collapse. It becomes even hotter in the core than it was initially. The next heavier atomic nuclei starts to fuse. You have radiation pressure again. It expands the star out. And that's well and good until it runs out of that fuel. It starts to collapse again, and it keeps doing that, pulsating back and forth as it runs out of one fusion product and then forms another one. So it gets as far as carbon for a star of this mass. Once it gets to carbon, when it collapses, it does not get hot enough for carbon to fuse. So that's the end of the star. It collapses, the core gives it, which is collapsing faster than the atmospheric layers of the stars around it. When it collapses, it kind of goes a little bit past its equilibrium point, bounces back out with a little rebound, meets the infalling atmospheric material, and puffs it off into a planetary nebula. Planetary nebulas are very transient. They only last about 50,000 years, and then they have become so tenuous and spread out so far into the interstellar medium, you can no longer see them. All you have is left behind is the white dwarf stellar core. The white dwarf is held in equilibrium by Chandrasekhar's limit. There is a limit to which a white dwarf can remain a white dwarf. As the core collapses, the atoms are pushed tighter and tighter and tighter, closer and closer together until you have electron cloud against electron cloud. Every single possible electron position is filled. There's not room for one more. So the electrons are repelling each other. They are strong enough to withstand gravity from collapsing the white dwarf any longer because there's not a huge amount of mass in these stars. So as long as it is, around 1.4 solar masses, it can withstand the gravity. And that is called electron degeneracy pressure. And that keeps a white dwarf, unless something else happens. Aquila, or Altair, is the next constellation. It is an A IVV luminosity class star. So it is 2 classes more massive than the Sun is, and it is has transitioned slightly off the main sequence. That is one of the stars that is part of the asterism for the Summer Triangle. Next is Auriga, that has Capella, and the hat on the charioteer for Orion. It is a 4-star system, actually. What we actually see as Capella is 2 red giant stars. One's a K, one is a classification K, one's a G, but they're both 3, so they are both on the red giant branch together. They're so close together that they look like they're just one star as we reserve them here on Earth. There's also another binary pair of small red dwarf stars orbiting with the double Capella one also, so that's really a 4-star system. Boötes has the star Arcturus. Again, this is actually a red giant star. It's actually one of the brightest stars in the northern hemisphere above the equator. It is obviously, as a red giant, it is eventually going to produce a planetary nebula and a white dwarf. It is kind of an odd star because it's part of a little group of stars called the Arcturus stream. And it's just a little group of stars that are moving really fast, about 150 kilometers per second, perpendicular to the galactic plane for some odd reason. So eventually, Boötes will become closer to us, but then eventually it won't be in our sky at all, because it will just keep on trucking down the galactic highway. So next is Canis Major and Canis Minor. Kind of fun, Orion's dogs. Kind of interesting that the two really bright stars in these two constellations, Sirius and Procyon, both have are in a binary system with a white dwarf. So Sirius A is the big bright star Sirius, and Sirius B is the white dwarf companion. Procyon, again, Procyon A is the star we see as Procyon, and the star we cannot see in a binary system with it is Procyon B, the white dwarf. Carina has a couple of star formation complexes in it. NGC 3603 is a very young, hot cluster of stars, very massive stars. They are newly formed within, let's say, 3 to 4 to 5 million years old only, not very old astronomically speaking. They are about 20,000 light years away, which is fairly close. It just happens to be that between us and them, there's a very low visual extinction. That makes them very bright. They're very compact, so they're very easy to see and study. So a lot of observatories have done a lot of multi-wavelength observations of this particular nebula. And of course, we have the Great Carina Nebula, 3772, which is one of the most massive star formation complexes in the Milky Way galaxy. If you've ever heard of Eta Carina, which is a massive, massive star, supermassive star that's going to go hyper supernova any astronomical moment, is over here, this little bright white spot on the left-hand end of it. And you can see everything that is a part of a star formation complex. You see reflection nebulas, the blue ones that are reflecting the ultraviolet radiation from forming stars. You see the red emission nebulas where the gas and dust has been heated and they're emitting their own radiation. And you see the black clouds of gas and dust, the opaque clouds, which were where protostars started forming anyway, and now they're being carved and evaporated away by the intense ultraviolet radiation from the stars that are forming. There are at least a dozen stars right here that are 50 to 100 solar masses, so it produces some really massive stars. This is one of my all-time favorite observations in the Carina Nebula. This is two Hubble images, stunning images, close-up images to show you what's going on. That little kind of little spinning hat on top of that little pillar of cloud of gas and dust, that's being put out by a massive star that's forming right there in that little cluster. It's sort of like a little pinwheel looking thing. But if you look further down, you'll see some dark places where stars are trying to form, protostars are trying to form everywhere here. If you look at the one on the left, you see lots of little nubby dark patches with bright behind them, and those are all protostars trying to form. But most of them will not make it. Especially if you look at the close-up on the right-hand side, at the lower end, you will see where jets of material are being spewed out by massive stars forming. And most of those stars, the massive stars, are going to photo-evaporate away the gas and dust and destroy most of the protostars that are forming. Star formation is only about 10% efficient. Only 10% of all protostars actually become a star, and the other 90% get destroyed by the 10% that actually make it.